Welcome back. In topic 1, we discussed the 5 thermal fluid factors so that you will be able to use the roadmap to select the proper Newton number equation. In topic 2, we will present you the roadmap and the solution steps. A. Roadmap for selecting the Newton number equation. First, on the upper left of the roadmap, these are the heat equations. On the lower left of the roadmap, this is table 7.2. Second, when you use the roadmap, first, you need to confirm that it is an external flow convection problem and you're looking for the Newton number. Second, for the solid body interacting with the moving fluid, you need to determine whether it is a slender body or a blunt body. Third, for the moving fluid, you need to determine whether it is a laminar flow or a turbulent flow or a mixed laminar and turbulent flow. Fourth, for the solid surface, you need to determine the thermal boundary condition. Lastly, based upon if you try to find local Newton number or averaged Newton number, you select the proper equation for it. For an extra flow around a blunt body, like a cylinder, we're only interested in the averaged Newton number. There are 3 options for the Newton number equations. You can select any one of them, but be prepared that you may get different values of Newton number by selecting different Newton number equation. Keep this in mind. It is acceptable when we evaluate the Newton number with a 20% difference. B. Example 7-1. This example is designed for students to get familiar with the roadmap and the steps by filling out the provided table. Therefore, this example leaves to students' practice. C. Solution steps. There are 7 specific steps that you can follow to solve external flow convection problem. Yet, the best way to learn solution steps is that we solve the problem together by using it. D. Example 7-2. An experiment was conducted on a cylinder with diameter D, length L. The cylinder is heated internally to maintain the surface at uniform temperature Ts. It is subjected to a cross flow of air at temperature T infinity and velocity V infinity. We need to find out how much power dissipation is lost through convection. This is the air property. Step 1, That's what we know and what need to be found. Step 2, we need to identify the heat transfer mode. There's a convection between the solid surface and moving fluid. The flow of air is around cylinder. Therefore, it is confirmed that the heat transfer mode is an external flow convection over a blunt body over the cylinder, and the convection occurs on the side surface of the cylinder A, which is a pi dl. Step 3, we select proper heat rate equation for the unknown convection heat rate. Since we know the surface area pi dl and temperature difference between the solid surface and moving fluid, if we can get heat transfer coefficient h bar value, then we will get convection heat rate value. Furthermore, we're interested in the averaged heat transfer coefficient and the averaged Newton number. Step 4, the rest of the work is to follow the 7 specific external flow convection problem solving steps to get H, then Q. 1. Identify which heat transfer coefficient is desired, local or average. From equation 1, we have identified that we're interested in the local or the averaged heat transfer coefficient and averaged Newton number. 2. Recognize the thermal boundary condition on the solid surface. The thermal boundary condition for our case is constant surface temperature. 3. Fluid property is provided here. 4. Determine the flow condition. We use equation to calculate Reynolds number. We plug into the numbers, velocity, diameter, viscosity to get the Reynolds number value, then compare with the critical Reynolds number. Since it's less, so the flow is laminar. 5. Select Newton number equation by following the roadmap. We have confirmed that it is an external flow convection problem and we're looking for the Newton number. Since it is the external flow around a blunt body of a cylinder, we're only interested in the averaged Newton number, and then we select Churchill-Bernstein Newton number equation, and it is represented in equation 3. Next, we plug into Reynolds number and Prandtl number into equation 3 to get the averaged Newton number. 6. Get H value. We use equation 4 to calculate averaged heat transfer coefficient, plug into number, conductivity, averaged Newton number, diameter, to get the averaged heat transfer coefficient. 7. Get unknown. We go back to the equation 1, then plug into numbers, heat transfer coefficient, area pi dl, temperature difference. Finally, we get the convection heat rate loss. At this point, we cover topic 2, how to solve external flow convection problems. We use example to show that you still can use the general solution steps plus the 7 specific steps to solve external flow convection problems, including using the roadmap to select proper Newton number equation to get H, then find unknowns. Next, let's do a bonus example E, example 7-3. There are 2 configurations, 1 and 2, for a heated compartment. Configuration 1 is made of smooth surface A first, then A followed by rough surface B. Configuration 2 is made of rough surface B first, then it followed by the smooth surface A. Air at temperature T infinity and velocity V infinity is passed over the top surface. The surface A and B are at uniform temperature Ts. We need to find out the heat flux at a specific location X, which is 1 meter, right here. For question B and C, they leave to students' practice. Air property is provided here. Step 1, that's what we know and what need to be found. Step 2, we need to identify the heat transfer mode. There's a convection between the solid surface and moving fluid. The airflow is around the top surface. Therefore, it is confirmed that the heat transfer mode is an external flow convection over a slender plate, and the convection occurs on the surface area A, which is 0.5 meter times 1 meter. Step 3, select the proper heat flux equation for the unknown heat flux. Since we know the temperature difference between solid surface and moving fluid, if we get H local, then we get heat flux. Furthermore, we're interested in the local heat transfer coefficient and local Newton number. Step 4, rest of the work is to follow the 7 specific external flow convection problem solving steps to get Hx and then Qx double prime. 1. We already identified that from the equation we are interested in the local heat transfer coefficient and local Newton number. 2. We have recognized that the thermal boundary condition for the solid surface is constant surface temperature. 3. Fluid property is provided here. 4. We need to determine the flow condition. When a flow over a slender body like a plate, there are three possibilities of flow patterns. A, flow is all laminar from the beginning to the end. B, flow starts as a laminar and then in transition into a turbulent. C, flow starts as a turbulent and remains to be a turbulent from the beginning to the end. How to determine these three possibilities of the flow patterns? First, we calculate the critical distance xcr by using the equation 2, where mu is the viscosity, V infinity is the velocity. Second, we compare xcr, the critical distance, with the length of the slender body. A, if the xcr is greater than L, then the flow is all laminar from the beginning to the end. B, if the xcr is less than L, greater than 0, then the flow is a mix of laminar and turbulent. C, if the incoming flow is turbulent, or the incoming laminar flow is tripped at the beginning, then the flow is turbulent from the beginning to the end. Now, let's apply the comparison method to our case. We use equation 2 to calculate xcr, then plug into numbers, viscosity, velocity to get the critical distance, which is 0.48 meter. It is right before the rough surface B starts. Since the xcr value is less than L, greater than 0, so the flow pattern is a mixed laminar and turbulent flow. 5. Select Newton number equation by following the roadmap. We have confirmed that it is an external flow convection problem, and we're looking for the Newton number. It is a slender body. The flow condition is a mixed laminar and turbulent flow. The thermal boundary condition for the solid surface is a constant temperature, and we're trying to find local Newton number. This equation is our selection, and it is represented in equation 3. Next, we're given with Prandtl number. We use equation 4 to calculate the local Reynolds number with V, X, viscosity. We get the Reynolds number value. Then we'll plug the Reynolds number and Prandtl number into equation 3 to get the local Newton number value. 6. Get H value. We use equation 5 to calculate the local heat transfer coefficient at a specific location x equal 1 meter. Plug into number, conductivity, Newton number, location. Then we get the local heat transfer coefficient. 7. Get unknown. We go back to the equation 1, then plug into number, heat transfer coefficient, temperature difference, then we get the local heat flux value. Hope you had fun. See you next time.